Welcome to homework.
Okay, so let's take a look at the parallel state first. So at parallel states, the corresponding energy can be equal to negative mu sc proton times b, which is equal to negative 2.7928 mu n times b. We know mu sc proton here is the z components of the spin magnetic moments, and mu n here is the nuclear magneton. So we know the nuclear magneton is equal to 3.15245 times 10 to the power negative 8 electron volts per Tesla. And we know the magnetic field is given as 1.65 Tesla. So now we can plug in back to the equation to determine the corresponding energy in parallel states for proton, which is equal to, let me see, negative 3.15245 times 10 to the power of negative 8 electron volts per Tesla times 1.65 Tesla, and then times negative, I'm sorry, not negative, 2.7928. And this will give us the corresponding energy in the parallel states is equal to negative 14.5269 times 10 to the power of negative 8 electron volts. So now let's take a look at the antiparallel states. So the corresponding energy should be equal to the negative energy at the parallel state. So if U2 is equal to negative U1, which is equal to 14.5269 times 10 to the power of negative 8 electron volts. So we know that the energy in the parallel states is less than the energy in the antiparallel state, since one is negative, another one is positive, and this will give us the parallel state of the proton should have a lower energy. So let me write it down. So parallel states has lower energy. So now let's take a look at the energy difference. So the energy difference should be equal to U2 minus U1, which is equal to negative 2U1. If you plug in the values, we'll have the energy difference between these two states is equal to 2.90537 times 10 to the power negative 7 electron volts. So we know the energy difference can be equal to hc over lambda or equal to hf. Lambda is the wavelength, f is the frequency. So if we do some arrangement here, we have lambda is equal to hc over delta E. So we know we can convert the energy from electron volt to joule, which is about 4.64859 times 10 to the power negative 26 joule. And when the Planck constant is equal to 6.63 times 10 to the power negative 34 kilogram meter squared per second. And we know the speed of light is equal to 3 times 10 to the power 8 meter per second. So now let's plug in back to the equation to determine the wavelength for the proton, which is equal to 6.63 times 10 to the power of negative 34 kilogram times meter squared per second, and then multiplied by 3 times 10 to the power of 8 meter per second divided by the energy, which is 4.64859 times 10 to the power of negative 26 joule. And this will give us the wavelength is equal to 4.28 meter. And then we can determine the frequency, which is equal to delta E over H. If we plug in values, we have the frequency is equal to 7.01 times 10 to the power 7 hertz. So based on the frequency and the wavelength we just calculated, the region that it should light in should be the radial region. So now let's take a look at the second question. So for the second question, our target is electrons. So at parallel states, the corresponding energy can be equal to 95.5 times 10 to the power -6 electron volts. And then at anti-parallel states, we know it's always opposite with the parallel state. So therefore, have U2 is equal to negative U1, which is equal to negative 95.5 times 10 to the power -6 electron volts. As you can tell, U2 is less than U1, which means that anti-parallel states has lower energy in the electron case. So now let's determine the energy difference between these two states, which is equal to 191 times 10 to the power -6 electron volts. So now we can determine the wavelength and the frequency. So the corresponding wavelength is equal to 6.51 millimeter, and the corresponding frequency is equal to 4.61 times 10 to the power 10 hertz. And based on the wavelength and the frequency which is calculated, so the region that it should lie should be microwave. And these are the answers for this question.